Good morning, everyone. Welcome back to the fourth day of the international webinar organized by Government Sampaio College on the theme of natural disaster with special emphasis to earthquake and its implications. My name is Nimsang Zwale, Assistant Professor, Government Sampaio College, Department of English, and I will be your host for the day. Before we start our program, I would like to remind the participants that the feedback link for today's session will be available during the second session. This link will be pinned in the comment section below. Your feedback will be taken as your attendance. And also for any queries and questions to the speakers, you may easily drop your questions down in the comment section below. Today, we have two speakers who will be presenting. Let me introduce you to our first speaker, Dr. C.Laldawngliana. Dr. C.Laldawngliana is an associate professor in the Department of Chemistry at Government Sampaio College. He boasts 5 years research experience in indoor radon monitoring and 11 years research in water monitoring. He has published 9 papers in peer-reviewed journals. His paper presentation includes 6 international seminars and 4 national seminars. He is a widely recognized researcher, and one of his research papers is awarded as a top-cited paper in 2011 and 2012. He has teaching experience of 21 years, and we are very lucky to have Dr. C.Laldawngliana as a resource person today. Today, his presentation will be on the topic radon monitoring for earthquake prediction. Now, let me welcome Dr. C.Laldawngliana to have his presentation.
A very good morning to you all today. And as our host has introduced about the topic for today, for my presentation, first of all, after 3 days long talks from different expertise knowledge about the earthquake on different corners. So today, I'm going to talk about the earthquake from another concept, how people are doing research work and correlating with the prediction of the earthquake throughout the globe. So today, my presentation will focus not in a particular research work. This will be a correlation of different research works that has been carried out to correlate between the radon concentration in the environment and the outbreak of the earthquake in different corners of the world. So I am just going to correlate all these data from the researchers from different corners of the world, and we will try to see how there is a correlation between the radon concentration changes along with the consequences of the earthquake event. This topic may be a little different from the other presentation, because I'm not going to discuss about the geology or the geomorphology of the Earth's crust. I am going to talk about different aspects, something which is related to the chemistry and the elements which is naturally occurring underneath the Earth's crust. So I beg your pardon to bear with me, I'm not going to discuss or present in a very technical things. I just want to simplify it so that even the common people can understand as far as possible. Of course, there may be some technical terms which are involved as we go along with the presentation. But this will be a very simple one. Even the local general public may be able to understand. So the radon monitoring for earthquake prediction is the topic for my presentation. We know earthquake, and we experience, especially these days here in the eastern part of Mizoram, which is not the event which we have experienced in before, because earthquake mostly we experience once in 2 years or 3 years, or maybe a little longer also. But the peculiar experiences we have this year in the midst of the pandemic COVID-19, we are stricken by a frequent earthquakes that we never experienced before. So this led the general public also panic to some extent, that we have already mentioned before also. And for this purpose, even government Champhai College is also giving a keen interest to educate and highlight some of the technical or scientific approach where earthquakes happened and the consequences of the hard earthquakes, so that the mitigation process can be set up to some extent. Of course, earthquake cannot be predicted in full, but at least if we have the knowledge to some extent about the consequences and the early warning system also, we may be able to minimize the devastating effect of the earthquake. So coming into the slide, before I go deeper into the topic, the yardstick which we are using is radon. So I would like to explain or expose you what is meant by radon or what it is. Radon is the naturally occurring element. It belongs to a zero group element in periodic table. It may be strange for some people. In periodic table, we have different groups which have been classified by the scientists so that different elements are arranged in a particular group having common characters and common properties to some extent. So they are grouping them in the periodic table. So in that periodic table, radon is grouped in the zero group element. That is in the extreme right corner of the periodic table. For the science student, I think this is very clear. And zero group means it is an inert group. That means which are non-reactive. So they are not reactive. The common zero group elements we have, we know are those argon, neon, xenon, krypton. All these are the common inert elements which are under the zero group in the periodic table. And radon is also having the similar characters with these elements. It has been grouped along with them in the zero group. And the peculiar character of radon, in comparison with the other inert gases is that radon is grouped among the metalloids. That means these metalloids are not purely metal, nor even non-metal also. It's in between the metals and the non-metals. So they have the characters to some extent, which is something relevant to the characters of the metals. And along with that, they have the characters of the non-metals also. So they are in between the two distinct groups, the metals and the non-metals. And here, radon, the existence of radon is the gaseous form. Though it is present in the Earth's crust, but the form of radon is in a gaseous form. And the abundance of the radon gas in the Earth is 1 part in 1 sextillion part of air. So being a gas, so it is mixed with gas. So if we consider its abundance, it is 1 part in 1 sextillion part of air. So it is a considerable amount. And radon, different from the other elements present in the Earth's crust, it is not exist as alone in original. It is existing as the decay product from the parent radioactive element, mainly uranium and thorium. So radon is the product formed when uranium and thorium decays, and where radon will be exist. And being the source of radon, uranium is very, very important, because almost all of us know that what is uranium, because it is familiar for its radioactive property. So it has been used for general public also. We know that for nuclear power. So we are very familiar with uranium. So this uranium is very, very important element, and the total abundance of uranium content in Earth's crust is 3 to 4 parts per million as comparison to the total Earth's crust content. So 3 to 4 parts per million. And among the uranium also, we have different isotopes of uranium, that is different types of uranium, we can say. This uranium-238, this isotope is the most abundant uranium among its isotopes. And it consists of 99.3%. Among the uranium we find, that means it is much, much higher in abundance as compared to the other isotopes of uranium. And its half-life is 4.4683 into 10 to the power 9 years. So it's a very, very long-lived element. Why we talk about half-life, I'm not going to in detail with this one, but let me just highlight what is meant by half-life. Half-life is the time taken for half of the original amount of the radioactive element to decay to its half. So that means when half of the uranium element present decays, that will take 4.4683 into 10 to the power 9 years. That is, we can just count about the duration also. It's a very, very long-lived. And the second most common isotope of uranium is uranium-235, and its relative abundance is only about 0.7%. So, and the rest of the other uranium isotopes are only present in trace amount. And uranium, as I told you, is the radioactive element. So it disintegrates by itself by emitting certain radiations, certain particles, so that it decays and it has been transformed into another element as it goes on decaying. So it has been broken up into different elements. Then this is the decay trend of uranium-238. Here, this is the original uranium-238, 4.5 gigayears half-life. And as long as, as it goes on decaying, it emits alpha particle to thorium, and thorium decays with beta particle emission that will transform into protactinium, and it has been transformed to uranium by decaying with beta particle. And again, uranium-234 has been transformed into 230 thorium, and then radium-226, and then radon, that is the element of our interest. So the course of the transformation is also very long here, but we know that Earths exist in millions and trillions of years ago. So the abundance of the radon in the Earth's crust will be enormous. And that will be effective for our yardstick to predict the earthquake occurrence also, and what the scientists are doing so. And this is again the thorium series. Here also radon has been formed along with the disintegration. And this is the radium disintegration. So here also we have radon. And coming into the radon, as we know, it is a product of the disintegration of uranium and thorium, and of course, radium also. And it is also a radioactive element. And it is an alpha emitter. That means it emits, as it disintegrates, it emits alpha particle. And the alpha particle is nothing but it is similar. It is not helium nucleus, but it is similar to helium nucleus. So we never call it helium nucleus. So it is similar to the helium nucleus. And as we know that this helium nucleus has a charge of +2, and that means this is ionic. So this alpha particle has been emitted from radon, and that is what we are using to monitor or to study the earthquake prediction by the scientists. And this is what we are using as a yardstick for the earthquake studies also. And we know that radon is an alpha emitter, and it emits alpha with the energy of 3 mega electron volt per nucleon. So this much energy per alpha particle has been coming out when radon is pushing out or emitting the alpha particle. So it is something which can say energetic. And radon also is having different isotopes of about 37 isotopes, but mostly they are very, very short-lived. Here we say the T-half, that is the half-life that I have introduced you before. The half-life ranges from microsecond to seconds, minute, hour, and days only, not even years. So the radon is a very short-lived decay element, decay product. And the most long-lived, the longest lived, I would say, radon is 222 isotope radon, and the half-life is only 3.82 days. So it can exists as a radon, for 3.82 days. And another one is thoron, which is 220, and half-life is 51.5 seconds. And another one is actinon, 219 isotope, having T half of 3.92 seconds. So these are very short-lived, so we cannot normally used for this kind of a long study for the precursor, as a precursor for the earthquake predictions. And how radon measurements are done. That is very, very important, because we are going to measure the radon concentration to study the earthquake event. Here we have generally common two types. One is passive method. The passive method, it is something like an integrated method where we use a detector. That is also a very simple one, which is called a solid state nuclear track detector, SSNTD. And that solid state nuclear track detector is also for radon measurement. We use a alpha active detector, because radon is an alpha emitter. That's why we have to measure the alpha emission. So it should be alpha active. And that one is nothing but is a polymer, which is called a cellulose nitrate film. So this is the commercial name. We call it LR115. And that is mostly commonly produced, synthesized by this Kodak Patek company. And this is commonly used across the globe. And this is, as I told you, is a cellulose nitrate film. And here it's being an alpha active. Whatever the alpha particle comes out from the radon, alpha particle will strike to the cellulose nitrate film. As it strikes, being alpha particle is nothing but it resembles helium nucleus. So it is a positive charge ion. So the ion will break the bond of the polymer, the cellulose nitrate film, and it will leave unstable site along its trails. So the unstable sites along the trails of the alpha particles will not recombine. So the unstable part can be traced out or can be identified by using a chemical etching process with 2.5 normal sodium hydroxide at about 60 to 70 degrees centigrade for about 120 minutes. Sometimes it may be a little shorter depending on the situation we are using. But commonly we used this process and this time duration also. And here in chemical etching, the unstable part of the alpha particle trails will be etched out. Then there will be a kind of what we say a spot, a white spot or hole, we can say, is formed, so that counting the holes in the cellulose nitrate film, we can estimate how much alpha particles are striking that particular detector. And that is also subject for a period of time. So we are fixing the period of time. So we are integrating how much alpha particle are striking the detector for a period of time. So the data which has been generated will be integrated with respect to time. So that is how the passive method has been employed. And another one is active method. That is, active method is assisted with electronic devices. So the common device we use is a scintillation counters. So the scintillation counters will record the alpha particles when it strikes and that will, the strikes of the alpha particle will be converted into a photoluminescence, and that will be recorded as a spark, as a counts by the detector, the scintillation counters, and that can be installed in any site where we feel that the earthquake is prone. So where we study the radon concentration for a period of time, we may fix per day, or we may fix per week, or we may fix per hour. Also, we can fix the time according to our convenience. So we can study how much alpha particles are emitted or present in that particular area in a particular time. So that is the scintillation counters. And another one is the ionization chambers. That is also kind of a device where the presence of the alpha particle has been detected by the ionization effect it causes to the gas elements, which is put inside the chambers. So by studying the ionization rate, we can see how much alpha particles are present at a particular site in a particular time. So that these are the two broad methods which have been used for detecting the alpha particles. And now we are going to correlate the radon concentration and the earthquake. Here, as I have explained, that radon being a gas element, it emanates from the Earth's crust, because the main source of radon is from the Earth's crust. Because in the atmosphere, we don't have uranium deposit in the atmosphere. So the radon is coming out from the uranium disintegration, as I have explained it in the previous slides. Here, the main source of radon is uranium, that is from the Earth's crust. So whatever present in the atmosphere is also the radon which emanates from the Earth's crust by different methods. So the main storehouse of a radon gas is the Earth's crust, which is lying beneath the tectonic plates also. So the radon is continuously forming along the along the disintegration of the disintegration process of the uranium and thorium. So it is a natural process, so you cannot stop it. It will go on disintegrate, emitting radon or different kinds of particles and elements. And after some time, when it transforms into lead, we know lead is a stable element. So that is, as and when only it is transformed into lead, the disintegration process will stop only. So that will take, you see, for the uranium, 4.5 giga years that will take. So during our time, it will keep on disintegrating, it will keep on forming radon, it will keep on striking us. So we can peacefully use this natural process as a yardstick for studying the earthquake also. Here, when radon is being formed, it is a gas, so it will diffuses inside the Earth's crust also, along with other gases or whatever medium it have. So it will diffuses in that medium, and whenever it finds some openings or apertures from the beneath the Earth crust, it will come out, emanates from the soil, and it will diffuses sometime with groundwater table or aquifers. So you can see the radon concentration even in groundwater and aquifers, and even in the soil also. And lastly, in the atmosphere also, it can directly come out without and without trapping in the groundwater or soil, it can come out directly to the atmosphere also, and it will diffuse us with the air in the atmosphere. So radon concentration in air is also actively measured, monitored by different group of scientists, even today also. So this is a very interesting branch of environmental research, which people are doing actively. And the radon concentration in groundwater is also actively monitored, and even the soil concentration of radon is also actively monitored. So with all this data from different group of scientists that they have published, they also correlate with the earthquake event. And now also we are going to present you how it happens and how the earthquake prediction can also be done with these simple methods. Here, the radon gas, as I told you, when it emanates from the earth's crust, it escapes and trapped in the groundwater and aquifers and in the atmosphere. How it happens? People, the scientists, think that how this radon will come out, because the earth's crust, we know it is plates binded. So the boundary between the earth's crust and the mantle, different layers are there, as the geographers and the geologists has explained clearly in the previous presentations also. So the chance of radon escaping is very less, so to say, because there is a thick layers of the earth's crust, and different layers are there. But as we have been told by the presenters before, the tectonic plates, the plate of the earth is constantly moving, and they are not joined in all cases. There are some breakups, so different plates are there. So whenever these plates are colliding or moving, interacting, then there is always a chance of a crack or a gap formation between these plates. So radon being accumulating in that area, they are actively seeking the chance to escape from that pressure. So whenever they find the openings, the apertures, by cracks, by form of cracks or gaps, whatever it is, it will emanate from the earth's crust, and they will come out to the atmosphere or groundwater or aquifers. So whenever the tectonic movement is severe or frequent, we can say, then the chance of emanation of the radon from beneath the earth's crust is increased. So whenever there is an increase in the radon emanation, then we can correlate that there is something seismic activity is taking place, because that is the only way where the radon will have a chance to come out from beneath the crust. So that's why whenever the radon concentration increases, scientists think that there will be a correlation between the radon concentration, which has been monitored with the tectonic movement. So thinking in that way, they feel that this radon monitoring will be helpful for the tectonic activity, the seismic activity beneath the earth's crust. So they try to correlate. They have done the research, different research, and that different data have been published from their findings. So thinking in that way, the first measurement of radon in terms of seismic precursor was dated back in 1927. So in 1927, the scientist starts this kind of experiment as a seismic precursor. So correlating with the radon concentrations, changes in the radon concentrations. And in 1927 and 47, the first measurement of radon anomalies in the groundwater were made by Shiratoi and Imamura from Japan. They are the Japanese scientists. So they have measured the radon anomalies, or we can say the changes in the radon concentrations in the groundwater have been studied. And in 1953, as I've shown in this slide, the radon concentration, the radon anomalies in soil was made by, again, the Japanese scientist, Hatuda, along the active fault zone for 2 years. So he is monitoring the radon concentration changes in the soil during this year. So people are actively doing this research for this particular focus. And as they are going on doing this experiment, they report the anomaly in the radon concentrations in soil where the earthquake strikes the Tonankai of Japan in December 1944 with the Richter scale of 8. So it's a severe earthquake strikes during 1944 in Japan. So that is also studied by the scientists in correlating with the radon concentration. Then they have found that there is a drastic changes in the radon concentration as and when the earthquake are striking. Sometimes before also there is a hike in the radon concentration that I'll come along with the graphs. And in 1956, Okabe, another Japanese scientist, showed that the radon in air close to the soil surface of the ground zero of earthquake has shown a significant increase. So Okabe has shown that there is a significant increase in the air around the epicenter of the quake. So he is also correlating with the radon concentration changes with the earthquake event. And again in 1966 in Tashkent, the earthquake strikes has been experienced with 5.2 Richter scale on 15th April. And that is also studied by the two scientists, Ulomov and Marashev, along with their teams in 1967 and 1968. They have reported that the aquifer of the hot mineral water, 1300 to 2400 meter deep in the artesian basin of Tashkent, the radon concentration increases abruptly before a few months of the strikes. And that area, that center where they are doing the research was only about 1 to 2 kilometers from the epicenter. So they have traced out the abrupt changes in the radon concentration before the severe earthquake strikes that area. So people are actively doing this research work. And here is the presentation made by this scientist And this is uploaded by Marcos Santulin in the papers. Here, we have seen that from 1956, 57, 58, 59, 60, 61, till 65, or I can say that till 60, there is hardly appreciable changes in the radon concentration here as we go down, as we see the graph. But right from 1960, that means 6 years before the event has taken place, the radon concentration started increasing. And then in 1961 to 62, there is a appreciable hike in the concentration increases. And then it goes on increases. And in 1965 to 66, just before the event takes place, you see that there is an abrupt hike in the concentration of radon. So that tells that there is a severe movement takes place beneath the earth's crust, so that the radon also have chances to escape from that area to the surface or to the groundwater in bulk. So that is what is correlated here also. And then again, there is an abrupt decrease. That means the decrease again here implicates that there is a closing of the tectonic plates, which was open before. So there is a movement of tectonic plates, active movement of tectonic plates. So whenever it closes, then the radon has no chance to come out. That's why abruptly there is a change or decrease in the radon concentration in that area. So, and just after that one, the severe strikes happens. So that is how they are correlating. And this is the post or after shock radon concentration again. And here is again an interesting findings made by some scientists in Sandpoint, Alaska, February, where the earthquake strikes on 14 February 1983 at around 6.3 Richter scale. And here also, they are monitoring the radon concentration from a distance of 176 kilometers from the epicenter. So here, they are doing in 4 stations, research stations, where you see that there is ups and downs in the radon concentration from April, August, September, October, November, December in 1962, and January, till January, we see, we'll look into this one. Here, before January 1983, that means from August to December 1962, there is ups and downs in the radon concentration. And nothing happens. But as we enter in the new year of 1983, in January, you see an appreciable hike in the radon concentration. That is a month before the event strikes, that takes place, the earthquake takes place. So there is an appreciable hike in the radon concentration in all the 4 stations. And then there is a decrease again, then a slight increase again. So at that event, the earthquake strikes. So that is what they are reporting. And this is again an interesting report that we have, that this Igarashi et al. Has done in 1995, where the earthquake strikes in Cope, January 17, 1995. This radon monitoring is also done 17 meters deep in the well, 30 kilometers from the epicenters. And here we see that till 1993, the radon concentration was coming into a standstill. I mean, we can say stable at around 20 kilobecquerel per meter cube. And as we enter into the new year of 1994, then there is a record of a hike in the radon concentration, but it is not very high, we can say. There is no abrupt changes, but still then there is a record of a hike in the increase in the radon's concentration along the months. So, and then it increases and is as we enter the December month in 1994, then we can see an appreciable hike of around 100 becquerel per meter cube. And then during January, early January 1995 or late December 1994, from that point, there is a remarkable hike. And then you see here in the month of the January, here there is an abrupt increase beyond 200 becquerel per meter cube, around 250 becquerel per meter cube. A sudden increase takes place. And just after that, there is a sudden decrease in the radon concentration again. So a sudden increase and sudden decrease, sharp changes is taking place. And here, at that moment, 7.5 Richter scale earthquake strikes that area. So that is recorded by this group of scientists and correlating with the earthquake and the radon concentration. And here is another findings in Italy. Two stations, one is in Rieti station and another one is Rome station. Here, in these two sites, the earthquake takes place in 1980 September. 1973. That is a place called Luhuo. And no, this is not the one. Here, 1979 to 1980, the changes in the radon concentration in those areas. Here we see that there is ups and downs again. But as it approaches closer to the event, we see the appreciable hikes in the radon concentration in all these months. And there, the strikes takes place with 4.1 Richter scale. And this also shows that there is a changes in the radon concentration as the earthquake is processing for its strikes. And here again, interesting findings done by another group of scientists. Sorry. That is in Luhuo earthquake, 1973. Here, the Richter scale is 7.9. It's a very severe one. And this changes is just 8 days before the strikes takes place. Here we see that in 1973, from 2nd January, the measurement starts, and then there is ups and downs again. And February 1st, Here, this is the February 1st. Before that, there is an appreciable hike. You see, this hike is too much as compared to the other concentrations. So after that, there is again an abrupt decrease, change. And the strikes takes place after that one, again with 7.9 here at this point. So that is how it takes place, and that is how it happens. And here, again, the radon concentration in air of Cope earthquake in 1995 has been also monitored. And here we see that there is always an appreciable hike in the concentration just before the event takes place. So that is the radon concentration measurement even in air also. It means the atmospheric concentration also show appreciable change in this particular earthquake strikes. Here is also another one, a Tohoku earthquake. Here again, I'm not going very much in detail now. Here we see that Tohoku earthquake happens after the appreciable hikes takes place in all these the signals, the graphs, the readings. And here the radon concentration in soil in Italy, the Casazzo well, as reported by Martinelli et al. 2013. Here you see all this, what to say, purple or pink. Pink signals are the radon signals. And this deep blue are the earthquakes events. So no numerous number of earthquake strikes has been accorded. Here, you see, the appreciable changes in radon concentration is followed by the earthquakes. Sometimes it may be low magnitude, but sometimes it happens in a catastrophic scale also. So this is how there is a changes in the earthquake and the radon concentration changes. And here, again, I will just quickly present this radon gas in soil by Crisco Basin. Here, the earthquake takes place with a magnitude of 3.2 Richter scale and 1.8 Richter scale. Here, similar to the previous findings, there is a change in the radon concentration, appreciable changes in the radon concentration again, that is followed by the strikes. And here, I would like to present the indoor level and earthquake. In all these slides, I have shown the radon concentration in the outdoors, in the atmosphere or in the aquifers, groundwaters, and soils. But now the indoor radon level, from there also, the earthquake strikes can be studied and may be predicted beforehand with respect to the changes in the concentration. Here, the deep red is the daily peak, and this one, the blue peaks are the daily average peaks. And this one is the seismic magnitude, the seismic. You see, here, numerous strikes happens from 2.4, 2.3, 2.1, 2.7, like that. So a continuous strikes has been accorded with the radon concentration changes. Here, the maximum from this data from this graph or from this presentation, we find is this one, where the radon concentration is going up to 96 becquerel per meter cube, that in indoor. This is a very, very high concentration of radon in the indoor level. So there is an abrupt changes in the radon concentration, again, even in indoor also. So that has been followed by strikes of 3.3 magnitude. Rest are around 2.1 to 2.7, so it not even reached to 3. But here, the highest peak has been followed by the strike of 3.3 Richter scale. So that sometimes they say that even the magnitude of the earthquake event can also be related to the rise or the peaks, the height of the peaks in the radon concentration. But that is not very certain, so we cannot just say with authority that this is happened, this is what it is. Sometimes it may not always be, because there is no specific authority to make the yardstick with a rigid scale. So this is done by Jae-woo Kim et al. And has been reported in Nuclear Engineering and Technology 2018 in page 512 to volume 512 in page 218. So this is the reference. Here again, there is a remarkable findings we have seen. This uploaded by Boris Mazek. Here the magnitude 2.6 is, and the research site is 8 kilometers. So the peak here again, highest peak has been found around 20 kilobecquerel per meter cube per day, just 14 days before the event takes place. So this green area of the signal graphs are the changes that happens within this 14 days before the strikes takes place. So this again shows that there is a positive result that can correlate with the earthquake happenings along with the changes in the radon concentration. So with all these presentations and the results from different research groups, we find this radon monitoring is showing a good result and finds to be an effective indicator for the crucial activities such as earthquakes. And in all the data and the figures I have shown that radon concentration is the common character before the tremor strikes. The hike in the radon characters, the radon concentrations. And the magnitude and time of the tremor strikes cannot be correlated with the radon anomalies. Of course, there may be some consequences, or the coincidence may be there, but we cannot say that the magnitude of the strikes is directly related to the hikes in the radon concentration. We cannot say, because there is always a change. That's why, and we cannot make any conclusion in that respect. And from those presentations, we see that radon anomalies can be correlated to the occurrence of earthquake. And there are many other things that has to be done to make an appreciable result for the forecast. And radon monitoring alone will not give a perfect result, a perfect indicator for the event to take place, but this will give an appreciable remarks that something is happened underneath, so that even earthquakes can happen anytime when this hikes in the radon concentration is observed by the investigators. So one can say that there may be a possibility of earthquake strikes. So if something is happening in that way, then it may be a wise advice that people may have to get ready, or we can say aware, that anytime there is a possibility of the earthquake strikes, so that we can prepare beforehand and the devastating effect may be mitigated. So with this presentation, I end up my today's presentation. So thank you very much for your kind patience. Thank you.
A very warm thank you to Dr. C.Laldawngliana for your wonderful presentation. I hope that your work today is beneficial to all during a much needed time. With that, our first session has come to an end, and we will be right back for the second session at 11:45. And I hope that you will all join us for the second session as well. Thank you. Welcome back to our second session of Government Sampai College's international webinar on natural disaster with special emphasis to earthquake and its implications. We apologize for a short interruption due to a technical problem. Thank you for your patience. Our speaker for this session is Dr. Rebecca Ramaswamy. For a brief introduction about our speaker, Dr. Rebecca has a bachelor degree in technology in civil engineering from Jawaharlal Nehru Technological University, Hyderabad, and a master's degree in technology in structural dynamic earthquake engineering from IIT Roorkee. She has been awarded a PhD in civil engineering from IIT Delhi. She has joined Mizoram University as an assistant professor since 2014 at the Department of Civil Engineering. She has engaged in various site-specific seismic hazard analysis in and around New Capital Region in Delhi. Today, she will be speaking on the topic, Case Study, Seismic Hazard Study in Mizoram and its Vulnerability Assessment of Civil Engineering Structures. Now let me welcome Dr. Rebecca to present her paper.
Mình should hear more. Kalom the toke. Rebecca. Asay Rebecca Ramaswamy kanya MZU Assistant Professor in Civil Engineering Department kanya. Voin hianin ka topic ron sai turchu seismic hazard study Mizoram ron sai to angkhan ani. Eta kan cover turchu enge seismic hazard ania enge Mizoram eng mani learning kan eng tinge kan structure te akhoi chiata eng ang structure hinge kan tan cha eng ang hinge chalauti te kan sei don ni John ama sabera chanin eng seismic hazard hiti I enila learning hian ama top hianin I liền hình hiện ama top hian min ti bai thein min mi hring hi ati hlum lawa ma se seismic hazard kan ti liền hình awanga chiat na lo thleng te hian kan nuna te aswa thina hei hi eng awangi nge ni theyang tia kan en chuan leimin wangte leikhi wangte kan structure him tok lo wangte le liquefaction wangte ni theya chu tiang ho I chu seismic hazard kan tia hei tiang ho she thiam tur hian seismic hazard analysis kan ti thinin hei tiang ang ho mang seismic hazard analysis mang chuanin lir ning alo thlan huna po engtinge kan in le lo te ka him theyanga engtinge leimin te khan kan in le lo te aven theyanga engtinge khamin le kha chakna zok kan pek theyanga kha tiang te kha azir thei ta ni seismic hazard analysis hian tuna big hian chuan a structure failure big khami lir ning awanga lei chakna manga lir ning awanga chiat na lo thleng thei te kha engtinge seismic hazard analysis anti chen ti te kha kan sei do ni chuanin ton malamin seismic zone 5 kan omanga tinge lirte a hi ngai lawa kan te tuna ron hi zot zot ta chuwang khada changa kan sha the em chu khoilai ma hi lir ning thlang thei lo ram hi om lawa chuwang chang kho is seismic zonation 2000 po khanin ama lam khachuan seismic zone 1 to 5 kha om chinin zone 1 kha chuanin lir kha agin thei don lo re reng kha an ti china ma se tuna chuanin zone 1 kha an pe to a chan chu lir ning hi tectonic plate remote movement kha ani theilo ani lo ve thei ta ni khu lampang south india lampang ate chuanin clear ning om theilo tur zone 1 kha an pe thina ni ma se the three dam wang te khanin dam a khan tui kha a kho na se me ma khami khan lir ning vibration te kha lo siama khata khan lir ning te na kha lo om ve the ni kha wang khan khoi lai mai ko ve la hian lir ning wanga him lo thei om lo khan te ta ni chuanin mi thiam te chu dan chuanin kum tin hian million ni million hi ve lir ning angin shad ni a ma se kan call seismogram kan ti te hianin noi nga ve hi she thein machine in kan sha thei chu noi khat vel bor ni hian an she a chu tiang zinga a za vel bor chu chuanin damage kan ti in chiat na hi anon thlang thei thin ani chuanin khami awang khan seismic wave kan sha thiam hi angai em ta ni seismic wave lir ning ton chuma lir ning ate po second thum chu hi nga lom second ruk chu hi nga lom ta kan ti ta ni ma se kha kha ni re nim ti kha time history chang khan kan shi thei ta ni lir ning record a chang khan hemi lir ning record hi han enila input hem o khat kha p arrival time kan ti kha khami wave kha p wave kha aron in chan chi ati na ni ta chuanin in kal le cha s arrival time kha ron i ta ni s arrival time hi in law kan in le lo tan chan apoi mo em s arrival time hi ke ni machine in kan shat ve the li ra ning kan ti lai ang kha ani ta ni khatia api khau zong kha kan feel chhun chung kha ani beta api lo zong kha chu ahing to lawa mo kan ti hun kha ni ta ni chu wang chuanin anwai graph ate po hanin mo chuan a distance zir khanin khami p wave arrival time le s wave arrival time ha kan shat hiam thei don ta ni chuanin s wave kan thiam kan shat thiam kha angai ta ti na ni chu civil engineering structure b ka chuanin ta han en le taila inge p wave chu ni reng inge s wave chu ni reng ti kha kan en chuanin p wave kha chu in sha chu angin compressional wave ania eti hian aron compress phei kha ni aron compress phei ta khami kha chu hey acceleration amplitude posan lo hetia kan en chuana graph khala han enila chu wan chuanin kan structure kharong khoi phalo tani s wave kha chu in mangin he ti hian ron kalta kha han in le lo kha aron khoi don ti na kha anita ni bo chuanin plate tectonica hankal le tadi na ma lai kha chuanin kan anrin dan kha chuan heti hian kan ram leilong zong kha ain zong khom vek ta ni chuan kha hamwang changin kum million tam tak nu khanin aron adara chuan a hnuwa han aron in zom khom le a an titani chuanin hei kan sha thau angin Indian plate to Eurasian plate noya lutin Burma plate sira khatikhan aron in hnol lut pheita khatikhanin aron lu zel khanin tlang terote hetiaron in no lut pheina na ha chu tlang terote te kha aron siam te chu meya chuan kha wang khan theim kan Mizoram te po tlang ram kan te tlang khoya po ther seng sunga kha plain boundary in law kan samdak restriction zone kan omwangin khatikhan kan Indian plate kha Eurasian plate noya alu wang kha ditani chuanin lir hing lampang zer chiang ha chang kan hre ka nga hei a plate boundary hawa khan lir hing kha om lu ta em tani a chan chu a chet reng wang ti na khani me tani kha wang khanin hei Mizoram te chu an enila asira Burma plate le Indian plate inkara Eurasian plate te ho inkara han kan om tani kha wang khan kan che du em chang kan tectonic plate hin en kan te India tectonic atlas hin en taila notice chu hei a thur sung mai ni tlang shang fall shang khan India ram nang te chu enilang chuanin hei fault mang om lo re nga notice bi ka chon atam em meya kha wang khanin IS 1893 2000 chuanin zone 5 min da tani hemi me phian en wangila kan notice pum pui hi chu zone 5 min dan chan chu tuna kan sei to ang khan a stress tamna leit noya lu kan tamna mun ani wang khanin khati khanin tlang te kan nei sing sungin fault te kha tam em ani chuta Mizoram chu kan la wan dwai le zela landslide zonation me phian anila a sen tak po le khanin landslide an sa ti na khani le me Mizoram big te chu hei a sen em hei wang hianin lir ni mi bian mai hanin lei min hi hloma lir ni nga wanga lei min hi hlom bok ta ni chuanin hei tuna kan sei tong khanin notice tiang lai bi ka han chan fault hi tam em hei tiang hi seismotectonic atlas sisat atlas atanga kan thil mu fault shang kan mu thei khan ta ni chuan lira lo in kan ti hianin tunlaya an sei na satel tu aftershock foreshock main shock ti khani tani chuanin engtin nge hemi hi aftershock kan tia hi main shock kan tia hi foreshock kan ti bi kan tia sang berte ni lo ti so ma lai 1974 khang garnier and knock off chuanin distance and time window khan lo siam to tani khami distance hunga li ri zong kha aftershock le main foreshock kan tia khami window chung om lo zong kha main shock kan tia chuanin hemi te garnier knock off algorithm here 2012 le 2016 na SSHSC Seismic Senior Seismic Society of America ho khanin chu seismol en law leilung zir chiang tu ho in zom khom ho alian pui tu hnuwa lekha kan chharna sat ho po khanin anma ni NGA relationship next generation attenuation relationship tana an rin ngam kha anitani chu wang chuanin hemi distance and time window in an entaila midang dangin a modification hi chun siam to tani chuan a graph ma sa kan huang hianin line hnuai lampang zong ami hi chu aftershock le foreshock khan thei tani line chung ami tin zong kha a main shock ang khang kan treat thei tani mo khat khan aftershock le main shock chin chu kan she thei don tani chum chuanin hei Mizoram area han chuanin lir ni hi al tam lawa chuwang chan hemi ti po hian entaila earthquake catalog hi chuanin adot lia chuanin engi ngatinge khatyang zong kha civil engineer ta kan in le lo ta na apoi mo na chan kha kan enangai ta ni chuanin tuna kan topic seismic hazard chu a wave zir chiana khami wave kha engtinge kan structure hang kan lak lu thiang ti zir chian na kha number 1 na kha leilung atang khan apoi mo ta em ta ni chuanin kata khatwanin seismic hazard analysis pa ngai geologist te seismologist te khatyang hawinan ti ang kan shia thiam kha ngai ta ni chuanin kan structure kan implement theidan to kan man theidan to kan ngai to ngai ta ni adata chuan topographical amplification kha kan ti ta ni tu ler hinga te point hianga ahmuna zir khan anna in an lo ni in chenom lu ko kha anin na thlei ta ni topographical amplification chu lei chung rila away travel path away from in increase near decrease theidan kha khami kha lei chung ril kha kan ne sha thiam ngai ni adata chan soil amplification kan tia a top layer 30 meter vel chin kha engza ding nge ain amplify thei don kan lei hnuaya kha ain amplify don in de amplify don ti kha kan zir chian le kha ngai ni chumi hnuwa chuanin kan in sakna hmun tura khan slope stability te ngai donin in lo kan lei min wang hyang kan in a hnol donin ti te kha kan zir chian kha ngai ta ni a to bera chan eng ang structure nge kan man dona eng ang vulnerability nge kan structure man tura zir khan anei ti kha kan zir chian kha angai ta ni mo chuanin nachina khan kha ground motion shang shang kha kan sei to ta ni hi hmun shang shang a lir hing kha ni ta ni chuanin a image pahni na le a hnuai pakhat na le pahni nen en big taila hi gangtok lir hing 6.8 khami kha anita lir hing pakhat vek anya kha a site specific point mo na kan sha theina na ni Sikkim ti to pa chan 0.28 g chau kha maximum kha 0.28 g ania chan a peak po atlem a peak po 30 seconds nuwa chau ron kal himo chanin adot le hi han enila 1.6 g hi maximum ni le de away from kaldan hi adang le de tani changeng tok chu hi lo en le away from kaldan adang zil tani anasa khatam tal to kani geng tok chu a hian omzia chu a leilung kha hemi pathum ground motion kan da hi station shang shanga an record khani tani lir hi omna mun atanga station pathum recording khani tani chu wan chuanin a wave travel part kha sha thiam ngai tani chu wan chan in kan sakdon ring hemi ground motion himan tora ti ringot theilo tani kan leilunga zirte kan sakna tor pun zirte khanin kan en thiam kha ngai tani achang chu earthquake recording changpon kan hmu thiam mei tor himo ani tani chan chumi zolnia chuanin eng ang structure hinge regular structure ti a lir hing laka him da hleka kan ngai kan ti chuan symmetrical structure hi du thu sam ani symmetrical structure kan ti chuan alai taka philila a le lam kha an la in an che chang kha tiang ha symmetrical structure an ti ni chuta chuan a center of mass le a center of stiffness kha alai taka omanga omzia chu a khoi lai po khanin a building po dang khain an do na wangin sakdan mumal taka sak chuanin lir hing kha continuous load part localin a local chinta omzia chu a foundation changin a bi ma ron chhauta a bana ron chhauta chuan a bi ma ron kal ta slepa kala a slepa kal zo banga kala chuanin a banga kal zo khanin bi ma kalle in ake ya lut leina foundation a lut tur ani ta ni awi fa kha khatia lo lu chuanin chelai po mangdon lo ta ni ma se continuous load part kan ti lo chuanin abana khati khan abana ron lu chawanga aban khan alo do zo lo chuan aban kha chmei dona ani lo chuan abi ma chhaulenga bim kha chak chuanin adot le khana kanga a chak lo khan abi ma khan abim kha chhle dona chuanin abim kha chak tok chuan khati khan abanga lo ta tun lir hinga te po in hunga abanga de hlir ni kha khalni chu omzia chu a continuous load part kha amu mal tok lo wang ani theya chuanin abang kha a that a chak tok lo wang ani thei bokani chuan hei a figure noi ber rin kwalin en chuanin building pahni oma alaya kotero te om tani hei hinga tinge kan ti chuan building hi L shape te kan sakdon chuan claim te spacing kan da ngai ni one story ni chuanin inches chan ve katikhan chu story ni chang katikhan dimensions yam tur is kind of perfect is code kind of perfect tani chu kan zir chan ve ngai tani kan building kan sak sam du da na zir khan chanin eng hang hingi irregular structure tia eng ang hingi chalawati khakhan an le taila hey a figure setback structure kan ti achung apathum na yan anila hey tiang che chuni lo nangin mizo in saka hianin achung ron lor ta te atam em tiang a hianin aron in hip na to thin ta ni a continuous load pa kha aron ti buai ta khata hanin chiat na kha aron a energy kha ron in concentrate ta tiang na khan atron chedu ta em ta ni chonin anwai tiang lai kan ron chedu ta em ta ni chon anwai hin en le te he anwai soft story ni he engma ban cho om ta ni he mu tun ler ning te po khanin mu chon tiang lai he tiang building a han khi khem ti te kha atam du em kha thalak tin lo hu tong emuni hey tiang soft story te hi achalo ma chu ati dan te kan da sei chhoze langa chon he anwai ber he a kolom hi hei a thui hi hei tiang te hi lir hing la ka chon him lo te ta ni chan floating column kan ti me ya hei ti hian beam kha phaya thok le khata a ban kha ron chho le ru ta ban hi in nga na ni lo ta ni hei tiang chan mun chen thala phe cha Mizoram a chan hetia ban lo hianin ka ti hang cantilever thui tak sa in brick wall te kan rem le khaten lai te khanin chia khain concentrate du ta ni mo chan tu na kan sei tong khan khoi lai nge weak corner kan ti chuan hei a weak corner a zel khan chiat na haron thang do ni hei tiang lai tiang shape ni chuan tiang lai han chiat tiang lai hi aron chema big don ti shape ni chuan hei khatiang zel khan mo a shape zir khanin a chiat na in concentrate ta tur kha a zel ta ni kalai khan chiat na kha a energy kha in dissipate anga chuanin I aron chemei to don ta ni chuanin example han laila Butch earthquake 2001 mi kha Independence Day mi khamo zingdar somvela kha na hing ta khami chung khanin kan thel shat tur chu RCC building sakpa ngai sak thau kha achim manglo reng achim chan kha chu ke mani machine kan sak dan tiktok lo wang kha ni tani in chim kha chu om te me ma se in chim ho kha chu han en sian chon masonry structure kan ti RCC manglawa steel manglawa in reinforcement manglawa in sak ho khan ni mo chonin hey te yan anila building masazoki hey hemi hi water tank kanitani water tank chon enge tuya fok na sadon tani khatia lir lo him pe chon tuya fok na sanga khami wang khan hemi in hi achimi ni hemi water tank in chunga han da lo ta se hemi in hi a him pial don ni khami 2001 lir hing kha an sai dana chon a huna om te chon le khatia na ron om pop me aron ridur me yantia khami chung khanin kan in kha chhemanga lo minor repair box yam angai le tuklawan te kha 8.7 ni chuan hemi figures of pen anila abul vel mi chu him pian hi him lo chu ni ta ni atni him lo chan an ti chuan hei kan end point kan shingal me soft story building hei opening building ani hemo khatiang zel khana ni chuanin tunai khilam nimin velin tuipui ralama te kan han kala kan ngai thlang na sit chu Nepal earthquake ang hang kan ve me yang ti hi an boy na ber ni ma se Nepal earthquake po han enila thil re ngon compare don chuan kan leilunga in angim kan in sakdana in angim ti hi kan shat anga yani Nepal earthquake ang kha kan twar ve me yang em ti te kha zo na khatam ni Nepal earthquake ang kha kan twar theil khatia anga lian hat kan twar theil tok ma se kan omna hmuna zirin kan tuar dan kha in anga ngem o ti kha ni ta ni tu na han chan tuipui ral hi compare lo thei lo wa chan chu khata khan li rangi na sa tu na hi ti kha wang khanin khami comparison kha wang kha manga ai zol bi ki chu kan shat chu angin kan in sakdan te a him kan in sakdan te in don zu ting kan sa a kha ha chu kan le te han zo lo china nei the ta kha chu tun na tan ri chang ka sai tel ri lo me nga ma se Nepal le tuipui ral bi ang te kha han sai dun ta angila in Nepal chuan masonry kan sai tong thau khan masonry structure li athala kho khan enlet ula RCC frame structure pa ngai kha chu tuna athalo kan ti ang ho anwai opening na sa te long column te I khatiang chi masonry structure te khatiang do hlir khatiang RCC sak thapa ngai 10% potting lawang che ho kha za asom RCC structure thapa ngai ho chu achim ta ni chuanin hei tuna ka sei to ang khan hemi in te po zau khothar hei lama veng tu nei lawa hei lama bana oma hei khati khana kal ta zel khati ana hen ron khi ani me ya chuan hei po ban le bang in ka ra ron khi ta ni chuanin khati khan a weakest section a zel khanin a ron khi thil ta ni hei tiang lai phe chu leikha ron tlatel bok leikha ground failure kan ti kha aron om telawang khan hei a infield zong kha aron tlapop mai ni chuan hei hemi bi khin entaila retaining wall hi mizo pa fing pa ngai chuan tiang hang kan sat tu man kan sa to du lawani a chan chu hei in sha chu ang ading nil put meya hei tiang he chu lir hing lo po ni se hun te ra langa tiang om to he chu ni shim ta ni masal lim him wangin he ron in po ron po chok ta vak me ni a chhor do zong a step ang khan in kan do sham ngai ti na khan ni a step lawanga tianga ngil anga do ho kha chu a complain sei se lo kan sei se lo mang kha anam lo re ni khilama khan mo chuanin ka sei to ang khanin a continuous load part khanga ya abanga kalchuan chutiangin local failure ne nga chutiangin kanin le lo khana tuar lu tuk don lo mo bang thak te chu thil hau tak lu tuk ani lo ta ni dar hlang ke pon thak te chu thil hau tak ani lo ma se a structural failure kan ti chuan a reinforcement om chin a beam le a column ha kan sei ta ni a beam le column a po khan a column atia aban kamo column chu ban khan ta aban hi apoi mo per ta ni aban hi engti kong ma in a cheto ra ni lo ti hi ni ai in the earthquake resistant design of structure chuan kan ngai poi mo chuan a column hi engti zo mai na cheto ni lo tia a structure shima khan thil dang ho a in column kha fail ma sa to ra ni lo column a fail to china chuan in kha a him to lo ti na ni ta ni chu hei hemi figure te point and ula a column kha hei a fail chan ta mai ta ti na ni chu hei a khok ta vek to a chu wan chon a column hi arang thei ang mira replace angai ta ni chon hei te hi an column chan puinan khan heti hian an han war ngota a reinforcement te khat kan thiam lo chang kan du kan phwa chaw ve ngot hianin hei tiang te hi a ti chetu tam na hun tur ani don ti na kha ani don ta ni mo chuanin hei tiang te po mo a beam a ban hi engti kong ma ina chetura ni lo hi ania chuanin hei po anga la sang tok ta nin huang chong kha chong ni ang khan chuanin lira ging la kha a chen na sabi lu to ka ti han a chef vak me yan tia hei tiang hi chuan en zong re wat po han en ring wat po hianin in shet hiam me nga a him thei lo kha mi china po kan du lo ang chi ka ron sei to khanin a om kha chuan tiang lai han hei tiang lai hanin veng tu om lo le tiang lai han veng tu la om lo le nga la mo hei a sei to me pial ma khan a in ven nge khanga ni a bim kha phei ve thok khanga ni mo a bim phei po kha om lo kha tiang ta chu he tia la ding nil the te thil lo om ta kan ni zok ta ni chuanin khi lampanga anwar do pakha chu lintel beam ang dewa siam ma se brick a bok zonga a ma zonga tung zonga da si kha bok zongin an ron da thota khalai kha an in khi an sei han chan tiang lai a khi de ungi ni atam zo ka hana khi ni chan chu kan shed thru angin lintel beam chu tukver chunga kan da tukver chung chi a chung lampang atanga lot ron chuk thla lo veng tu tur kha ani ta ni ma se ta chuanin aveng tu tur ni lawin atirit tu anga khan kan siam ta tlot me a khatem te kha a thei sang chuanin tilawila tia kan ti don chuanin reinforce nge lintel beam ti dan tur takin a reinforce nge khan ti la khatia brick ti mut ai kha chuan brick ti mut big ai kha chuan mulo ve khan sia min a tlim chuan ala zia zo tho do na ni chuanin I retrofitting engting he kan siam that thiang tiang ho he I kan hmu ang khanin atam zo tu na kan hmu ang te hi chu bang siam that te chuanin a khi kha a sin viau chang kan han kher dewanga chuanin concrete cement chak deuh khanin kan han plaster chuan a thame do na ni chuan a then khat hei beam te column te a global failure to chin kha chu retrofitting te ti angai thri ni chuan chu tiang kan ti ma chuanin earthquake design philosophy hi kan hria thiam angai ani earthquake design philosophy hianin in hi a chere reng tura ni lo ate lo reng mo I minor earthquake ati chu 4 to 6 magnitude vel hi ani ta ni mo I 4 to 6 vela chuan a main member chu vertical horizontal forces carry to chu a beam le a column kha a chetura ni lo should not be damaged in ti ni ma se adang lai kha chu all something a siam that thein a repair thik tur ani atitani chuan moderate shaking ati chu 6 to 7.5 vel khani tani mo khatianga khan a main member ho po kha an chiat pon chu tianga siam harsa ani tur ani lo kha atitani mo chuanin strong shaking ati chen 8.5 chungnam pang hawa kha chuanin a column te kha siam that thei to lo ni ma se building kha atlu thut tur ani lo kha ti ta ni chu kan hria thiam thei dan tura chan kan in te hi le lama chuanin sut nga te a pangai taka in kan sa ni chuan pangai taka in kan sa a ani chuan kan reinforcement te kha pangai taka kan siam ni chuan in hi atlumi mi ngai bik lo nia hei in chim kan hmu to ho te po hi ngai to la lein a hnol tha te ni lo cha in chim shim chu atluk mi bik lo hi chu om zia chu adaptility kha anei thato ka kan in khan chu wang chuan atlu thut ngai lo ma se a kolom kha chak lo chuan a yan sa zok te po athleng thei tho ani internal sutli pali an manga in chong thum te sakan tum kha chuan kha tiang kha chu adaptility kha ni a in chakna han atin lo thei lu tuk ta ni khi lama mo an mang le sa ta ni ma se ka om zia chuanin mithiam te ron chungin thadwin kan in hi kan sakzel angai ani him tak kan om thei chuan nirging hi chu thil hla om tak ania ma se ega mani chena chia trup na te thing na te kan pum pel thei dan tu chu ki ma ni lam kan lo in ven vi a thiam zo te kan rona kan in thata ka kan ti te kan bungwa te kan bungwa te mi ron tla thei tu ho kil betila thil rit te chung sanga da la wila thil hok thei te thil ke thei te chung sanga da la wila khati khanin kan in shim ka chu him thei ni kan bang po lo ki tem ton po ni se chu tiangin ke mani lama ron kru te ni lo chuanin chu tiangin min tla do lo ni chu wang chan kan bang te kha min kluk phak lo na hmuna te khan om ta mi la kan hlo viau chuan mo chuanin retrofitting techniques kan ti chuan local failure le global failure kham ta ni local a chuan jacketing kan ti mizo pon kan war em rot kolom khatle mi kan kher khwa an pon bing hakle mi kan kher khwa a chuanin reinforcement ha kan dal a khatyang khan jacketing kan ti chu ni kha ha local failure ka khan kan mang thri ni ha kolom pakhata te a beam pakhata te footing pakhata te khatyang khanin kan mang thri ni chuan global failure chu a structure pum pui him na a khoi chiat structure pum pui him na siama ngai to china khan anita ni chuta chan shear wall te in nuai kha soft story kan tianga ta ka chuanin infields te kan siama nga chuanin bracing te po siam thei ta ni kha tiang ho zong kha ni ta ni mo chuanin jacketing chu he ka sei to ang khan tiang hi chu kan hmu thup to ka ringa Mizoram a hianin kan tina sat lu to ka kolom te kha duaya lo te mo duaya chak lo khan khati khan jacketing kha kan ti thina ni chuanin shear wall chu slab ang deuh hlek khanin reinforcement ha kan han siam banga khan retaining wall ai te po hanin kan hmang photo thin reng ani chuanin steel bracing hi steel lo pon i khilam panga chuanin wooden bracing te po khan lo tina sal tuka abi takin nin hoi soft story nei ho te kha an in te kha der thong lo nan le inge an parapet an veranda atwai i ban keng tu to si lo rit si kha tiang chi anga te khanin i alo bera thing sakhat deuh tal ten do ro ute kan tia puisa te hei kilama te chuan lo har sa ve le chong nen ani lo chuan puisa nei vele ba ngai takin banin siam chho do ne te kan ti ta ni chuanin kan ina soft story te mo enga moni chak lo deuh hlang lai chuan tiang te hian thing te mo thir te mo po kan tiang the ta du thu sama chuan kan concrete aya chak zok chu concrete a kan ti thela chuan a ai chak zok chu steel ni me ta ni mo ut ka chu en lo ti laklo thil thuwa thing kha chu laklo thil thuwa kan hmang thei ma se lo thu sama chuan steel kha hei he tiang sang sang ang hian in na moda na zir le rem chan da na zir khan in rem thei tu do na ni chuan base isolation hi chu thil hau tak tak hi nia Mizoram a phechang kan lo India rama po hian mun ni khat vela pak hian an ti lo ni i li rang hing hianin nge Newton law of motion chanati taksa resa chuan la res ringa toma motion chu motion a omatum omzia chu bas a te lo di bas ding la ya din chuan bas ding la ya khan ding ta ni lo in van in vak lo ta ni chuan aron tlan thut khanin hetian i taksa kha aron thlok phei thut thin ta i taksa chin kha ma se ike kha chu te na che ve ngai lo tero kha tiang khan lir hin chuanin structure kha om don tan nang ma om dan ang khan ake kha chula ding nge tum si kha na taksa kha phei don ta ni kha han chiat na te kha ron thlen bu em ta chu wan chuan base isolation kan te tiang hi dampers te bearings te kha tiang da khanin kha tiang da khan building ngai khan an da ta chuan lir lo hing pon a bearings ni pon a dampers kha aron cheta I building kha chu ading ngai khan ading reng mei don ni I chuanin adang le I building a rilu tu ka wanga hilampang aban hnuai lampang a chak tok to lo te khanin le enga moni boy na tam taka om khan mass reduction te po ti thei ta ni khilama te po in chong thumin sakatuma tia sutli pali chau tan lo hmang ta ni in chui sak le don chuan a hlom to lu tu ka te kan tia asam type ten sa to me ro ti lo chuanin thil rid deuh po da to lo me ro te kanin ti ni kha wang khanin kan thil saka khan uluk dewa kan engine kha ngai ni chuanin hei tiangai point chau hi chu in lo hu to me theya kan in sak do na thil poi mo te kan lei lai te kha bung tu ta ti lo to chhor do a ti tur kha tiang bok khan kan retaining wall po ka sei tong khan a chhor do zong a tang siam tum ngi tur chuanin kan lei lai te kha du anga a chak tok lo te khan le du soi nei ling te hi leikil te hi warila chuanin ban kha ka sei tong khan bi mai kha chak zo ngi tu na foundation te mi ti ang khan min fitli bia fitli thokin an tia kan thinam te pan te kan ti ve nge ti ri ngot thin la tur a thiam zok te tian lampang shethiam zo tian lampang thiam te kan ron lo chuanin kan in sak dan tur zir khan a foundation na mo tok ti kha lo umze la chu wang chuanin kha tiang ma ni res ve pup pup te kha a fu ber lo thin ni chuanin ka sei tong khan bim thok khau kha a chena salu to kani a chen khat pe chu tlak hluk lom te a chen khat pe kha chu tlahluk te po om ta ni chuanin leilon te po kha Zaukotar police station te ko han soi taira a building kha chheluk to kani khina sal tuk mas a slab kha a shanin staircase a step a khanin reinforcement shanin ban shanin an kalti rawang khan a step kha chemi alon ni amli chu inchunga khan omta ni se a building nen khan lo in zom ta se a step kha alo tule the inchung om te tang khanin dam chwangi na om lo ma se ban kha a shana om awang khan a ban kha lo a step tang khan himnam tak khan tlan tha thei me lon ta ni kha ten te kha oi mo lu tok ta ni chuanin tuilwan kor he Mizoram chang kan ngai poi mo ton in kan sakpon tuilwan kor kan siam ton ne kan in sira po tuilwan theilo turin chaddu in plaster kan siam zel torani kalome Ima zona omlam yang.
Question là ôm lem lâu thì mẹ là hầu question to someone. Question đầu khoa lúc kỳ là
Zona omlam chang kat loss me do na sin.
question cần ngọc lúc mà mình lòng lúc là đây lâu thế đủ tốt mấy con xem okay thì khoan nên question thì anh luôn zone là bạc hạt ở trong lô ta hay là giặc zone lâu thì thế là đồng học lệ ok là tôi này nha nín base isolation hi Mizoram ti chi ani ve em ti zona rum luta hi resource person ni na
Ti chi ni lo na chu omlo ma se base isolation hi chu a how ta glu to ka chu wang chu chuanin India ma po chu tiangin an lati lo chu tianga ti chi ni lo na chu om chuang lo mo ma se kan tlang aizol anga chuanin ti na vak boi thak me thea ma se khi lampang na mani lampang hei champhai ti vel le a chak lama ta chuan tle ma phai de uthak na chuanin ati thei lu to kang
kan zona hun kan ti tom me anga thank you to Dr. Rebecca for a stirring presentation. I believe that the participants and viewers will make good use of your presentation today. With that, we have come to the end of our today's webinar. Thank you all for participating to our program. I hope that you will join us for our tomorrow's final day session at 10:30 a.m. Thank you.
Thank you.